in the last lecture, we had started our discussion on registers and we looked at the design of parallel in, parallel out registers. Now, we continue with our discussion on the design of registers in this lecture also. Now, in this lecture we shall specifically be talking about shift registers. Now, I mentioned during the last lecture that a shift register is a register which has serial in and serial out shifting facilities. So, let us try to understand what this serial in, serial out and shifting facilities mean and how we can design a register with these facilities. Okay. So, talking about a shift register, a shift register is nothing but a register. Register means it can store, let us say a k bit shift register will be able to store k bits of data, where binary data can be stored, but additionally you can shift the data either to the left or to the right whenever required. There is a corresponding shift signal that can be used to do that. Now, what do you mean by shifting? This I will illustrate with this example that I have shown here. Let us talk about this example. Here I am showing a 4 bit shift register which is actually a right shift register. Data will be shifted on the right. Let us see how it works. Look, here also we have used D flip flops like a just like a PIPO register, and clock as usual is being connected in parallel to all the flip flops. But the way I have applied inputs to the D inputs of the flip flops are different. The first flip flop is getting its input from an external input called serial in. The second flip flop is getting the data input from the output of the previous. Similarly, the third D3 is getting from the output Q2, D4 is getting from the output Q3, and the final flip flop, the output, that you are calling as serial output. So, let us see that how it actually works. Let us assume that the data that is stored in this register are 1 0 1 1. Let us say at any particular point in time we have stored data 1 0 1 and 1, and in the external serial input I have applied a 0. Now, a clock comes. Now, understand what happens. This 0 is being fed to this input D 1, this 1 is being fed to the input D 2, this 0 is in D 3 and this 1 is in D 4. So, whenever this clock comes, this data will get stored in the flip flops in parallel. So, this 0 will get stored, this will become 0, this 1 will get stored, this will become 1, this 0 will get stored 0, this 1 will get stored, this remains 1. So, earlier it was 1 0 1 1, it was 1 0 1 1. Now, this external data 0 has come, now it becomes 0 1 0 1. Now, you see effectively initially I had 1 0 1 1, there has been a shift to the right, this 1 has moved here, 0 has moved here, this 1 has moved here, and some new data has been shifted in and the previous rightmost data has shifted out, right. So, in this way I can apply new data serial input once every clock and some new data can get shifted in one by one. This is essentially how a shift register works. Now, in this design I have showed how to use a shift register using D flip flops, but you can also use JK or SR flip flops. Like for example, if you are using JK flip flop, this will be J2 and there will be another input K2. So, there will be Q1 here and Q1 bar. So, Q1 will be connecting to J2 and Q1 bar will be connecting to K2, like this the connection will be there. Similarly, for SR flip flop, right. Okay. Now, there are some shift registers which have a separate shift enabled signal shift, and just like in a PIPO register we have used a load. So, either you can use a gated clock or using a multiplexer I can use it. So, in a very similar way I can use that shift signal in conjunction with the clock signal to enable the shifting. I can use the gated clock also, clock and gate, clock and shift. I can generate the clock signal for the flip flops, or I can use that multiplexer kind of a circuit that we discussed, right. Okay. Now, for the flip flop circuit that we have shown earlier, I am showing a so called timing diagram. Now, for sequential circuits, this timing diagram is very important to understand that how the things work. Here I am showing the timing diagram of a 4-bit register as the diagram you saw earlier, where I have assumed that the initial state of the register is 0 1 0 1. So, what I am showing in this diagram? I am showing the clock signal. Clock signal is coming continuously, and this red marked edges means this is the active edge, it is rising edge triggered all the flip flops, and SI is one of the inputs, serial input, and the 4 flip flop outputs are also shown. So, as I said, initial state is 0 1 0 1. So, it is 0 1 0 and 1. Let us see that when the first clock edge comes here, this value of SI was 1 high. So, this 1 will get shifted in, this 1 will come here, this 0 will come here, this 1 will come here, this 0 will come here. Next clock comes, this 1 will come here, this previous value of q 1, this will come here, previous value of this will come here, and previous value of q 3 will come here. Similarly, when the next clock comes here, now SI is 0. So, this 0 will come here, this 1 will come here, this 1 will come here, and this 0 will come here. So, there is a shifting that is going on, bits are getting shifted, q 1 to q 2, q 2 to q 3, q 3 to q 4. Right. So, this diagram whatever I have shown, if I want to show in sequence, so it will be like this. Initially the 4 outputs I am showing, initially it was 0 1 0 1. So, after the first clock it becomes 1 0 1 0. After the second clock it becomes 1 1 0 1. Third clock 0 1 1 0. Fourth clock 1 0 1 1. Now, see there is a shifting going on. You see this 0 is getting shifted like this, this 1 is getting shifted like this, this 0 is getting, this 1 is getting shifted like this. This is why we call it a shift register. This is the axis of time, right. So, with time the bits are getting shifted, this is q 1 and this is q 4, q 1 to q 2, q 2 to q 3, q 3 to q 4, and finally, one of the bit goes out. This is essentially what a shift register is, and this is how a simple shift register works, right. Okay. Now, there are several variations of shift registers that are possible depending on how you are connecting them. Ring counter, twisted ring on Johnson counter, bidirectional shift register, universal shift register, and something called linear feedback shift registers. So, some of these we shall be discussing in this lecture. Let us see. First, the ring counter. Well, the shift register circuit that we saw some time back, that is essentially a serial in serial out register. Here the data are not being loaded in parallel, data is being fed serially one bit at a time, and on the other side one bit at a time is coming out. So, we call it serial in serial out. Data is being fed one bit at a time, and data is also coming out 1 bit at a time. So, this was a SISO register, serial in, serial out. Now, ring counter is a special kind of SISO register, where instead of applying an external serial input SI, what we do, the Q output of the last flip flop we connect to the D input of the first flip flop. So, how does it look like? This will see. There are 4 stages, you just recall. There will be multiple stages of the flip flop. What we are saying is that let the shift register be connected as usual, but the output of the last stage we are feeding as the input of the first stage. This is what a ring counter is actually designed like. Now, typically in the ring counter we load with a single 1 and the remaining 0, let us say 1 0 0 0 or 0 0 0 1, because if you load it with all 0, so it will always remain 0, because the 0 will be fed back, again 0 will go in, but here this 1 will cyclically rotate, 1 will come here, then here, again come back. Okay. So, we shall see some typical applications of sub ring counter. We can use something called a multi-phase clock or some sequence of synchronizing pulses. But one thing to note is that for a k bit ring counter, let us say I have a 4 bit ring counter 1 0 0 0. So, after 1 clock it will become 0 1 0 0, after 2 clock it will become 0 0 1 0, after 3 0 0 0 1, and after 4 it again becomes 1 0 0 0. So, the sequence repeats after every 4 patterns. So, we call it a modulo 4 counter, mod 4 counter. So, for a k bit ring counter you can implement a modulo k counter. So, after this k number of patterns, the pattern again starts with 1 0 0 and repeats, right. Okay. So, this is how a ring counter looks like. So, here I am shown the diagram of a 3 bit ring counter. There are 3 flip flops, the output Q 3 is connected to D 1, and we assume that initially we load the flip flop with 1 0 0. So, this has 1, this has 0 and this has 0. So, if we again look at the timing diagram for this, you see initially this was 1 1 0 0 as I had said. After the first clock comes, there will be a shifting, 1 will come here, 0 will come, and this 0 will again come back here. So, this 1 will come here, 0 will come here, and this 0 will come back to Q 1. So, 0 1 0. At the next clock, this 1 will come here, 0 will be here and 0 will be here. Next clock again 1 is coming back, 1 0 0. Next clock this 1 again is shifting here, 0 1 0 0 0 1 and again 1 0 0. This repeats, right. Now, if you look at the kind of pulses that are generated in Q 1, Q 2 and Q 3, you see in Q 1 there is a pulse which is generated here, right, this, and remaining time it is 0. For Q 2 it is here, and for Q 3 it is here. So, if I consider this whole thing as my time period, then in this time period first Q 1 is active, then Q 2 is active, then Q 3 is active. So, I can say that Q 1, Q 2, Q 3 is generating non-overlapping pulse train, because Q 1, Q 2, Q 3 again Q 1 starts, again Q 1, again Q 2 and Q 3. So, in many applications we need something called multi-phase clocks, and using a ring counter we can very easily generate such multi-phase clocks. If you need a 4-phase clock, use a 4-bit ring counter and apply a clock of sufficiently high frequency, you will be generating the clocks from the 4 outputs. They will be shifted in phase, they will be non-overlapping. right. And just another thing I did not mention, you see from this timing diagram that whenever this clock edge comes, the time when this output of the flip flop is changing, there is a small delay which is shown, there is a small gap, right. This small gap is due to the delay of the flip flops, that a value has been applied and a clock comes, after some time, after how much time the output Q 2 will start changing. So, this gap that you see, for example, here, this gap actually indicates that delay, right. So, when you draw a timing diagram like this delay should also be specified, because the flip flops are not ideal flip flops. Whenever you change a clock, the outputs do not change immediately, there is a small delay after which the outputs change. Okay. So, this is how a ring counter works. Next, let us come to a very small variation of a ring counter. This is called a twisted ring or a Johnson counter. Now, in a ring counter, what we did? The Q output of the last flip flop we fed to the D input of the first flip flop. Now, in a Johnson counter, what we do? We take the Q bar output of the last flip flop, and that Q bar I feed back to the D input of the first flip flop. This is the only change. This is called twisted ring or a Johnson counter. So, as I mentioned, it is specified here, we connect the Q bar output of the last flip flop to the D input of the first flip flop. And in a Johnson counter, you can very easily initialize it to the all 0 state. I mean, unlike a ring counter, in a ring counter, if you initialize it to the all 0 state, it will always remain in the all 0 state, because none of the flip flops can become 1, but here it can become. And you will see that in a Johnson counter, the kind of patterns that are generated, zeros and ones are consecutive, which may be useful in some applications. And another feature is that for a k bit Johnson counter, I mean, it counts modulo 2k, like let us say for a 4 bit Johnson counter, it will generate 8 unique patterns before repeating twice of k, right. So, this I will illustrating with an example. Let us take a 4 bit Johnson counter as I have shown here. There are 4 flip flops. As you can see, I have connected the Q bar of the last flip flop to the D input of the first flip flop, and I am showing in the sequence of time the clock pulses what is happening, and I am assuming that the initial state is all 0. So, in this table, so initially the outputs are all zeros. So, 0 0 0 0. Now, just the only thing to remember is that the bar of the last bit will be fed to the first bit D 1. So, after one clock pulse Q 4 was 0. So, 1 was fed back. So, this will become 1, other zeros will be shifted 0 0 0. Second clock pulse, again this bit was 0. So, not of that, this 1 will be fed here, this 1 will get shifted, this 1 will shift 0 0, this will be shifting. Similarly, third clock pulse, this is again 0. So, 1 will be fed and these bits will all be shifting. Fourth clock pulse, again it was 0. So, again 1 will be fed, shifting. Now, the last bit is 1. So, now 0 will be fed, shifting, again 1, again 0 is fed, again 1, again 0 is fed, again 1, again 0 is fed, and you finally land up again to the all 0 state. So, you see there are 8 unique states that are there are 8 unique patterns which are followed, starting from the 0, 1, 2, 3, 4, 5, 6, 7, 8, 0 up to the 7 before it repeats again. right. So, this is something you have to remember, that for a Johnson counter, if we have a k bit Johnson counter, as I said, there will be 2 k unique patterns that you can generate. Now, there is another point that ones and zeros are consecutive if you look at any one of the output, let us say q 2. So, the patterns that are generated, I am looking at one cycle, see, you see all the ones are consecutive, they are together, the zeros will be consecutive, again they will be ones, again they will be zeros. So, the block of ones and zeros are all consecutive. So, in a cycle, say starting from here up to 7, you see ones are all consecutive, there are 4 ones, they are all consecutive. This is the property of Johnson counter, right. Okay. Let us now look at a more flexible kind of a shift register, bidirectional shift register. See, earlier the shift register circuit that we saw, it was a right shift register. So, the idea was something like this, there are 4 flip flops. So, we connected the output of this to the input of this, output of this to the input of this, output of this to input of this. So, it was a right shift register. But if I want to implement a left shift register, what do I do? For implementing a left shift register, the output of this one should be fed to the input of this, output of this one should be fed to the input of this, output of this one should be fed to the input of this, and output of this one will be the final output. So, this will be shifting left, this bit will go here, this bit will go here, this bit will go here. So, we will have to connect the q and d's in the reverse order, right. So, essentially the requirement is this. So, we need to use multiplexers so that the proper inputs are applied to the d, and I am assuming that there is a separate control input called LR bar, which if it is 1 it means left shift, if it is 0 it means right shift. So, let us see how the design looks like. This is the design of the bidirectional shift register. Let us see, there are 4 flip flops just like a normal register. Now, I have not connected q 1 to d 2 or q 2 to d 3 directly, rather there are 4 multiplexers I am using. Just see, all these multiplexers are having this LR bar as the select input, and I have suitably applied the inputs to the multiplexer. Let us assume I am trying to do a right shift, which means LR bar is 0. Right shift means the 0 inputs are selected of the multiplexer. So, this SI will come here, the SI will be coming here, Q 1 will come here, Q 1 will come here, Q 2 will be here, and Q 3 will be here. This is just like how we connected the register earlier, right? Q 1 was connected here, Q 2 was here, and Q 3 was here. Okay? This is normal right shift. But if you want to do left shift, then my L R bar would be 1. Now, if my L R bar will be 1, let us see what will happening. Now, it will start from the right side. So, my SI will be coming here, because my data will now be fed to the rightmost. Q 4 is coming here, just like I showed, Q 3 is coming here, and Q 2 is coming here. So, shifting will be happening in the reverse direction. Q 4 to Q 4 will be coming here, Q 3 will be coming here, Q 2 will be coming here, and Q 1 will get lost, and new value will be entering in Q 4, right. So, this is how a bidirectional shift register can be designed. A normal register where the inputs to D1 are properly selected by using multiplexers under the control of this LR bar. Okay. Now, the last kind of shift register that we talk about today in this lecture is a universal shift register. So, a universal shift register has some added functionality. So, it is a bidirectional shift register plus something more. So, what is more? What I am saying that the inputs that you are applying can be either in serial form or it can also be in parallel form, and also the outputs. Like an universal shift register looks like this. There are serial inputs available, right shift, left shift, there can be two separate serial inputs. But in addition you can also parallelly load the data. Now, in the shift register circuits that we have seen so far, there were no parallel data inputs that were there. Now, in this universal register, facility for parallel data input and also parallel data output both are also available. So, there is a D input which can be fed from outside, and there is a Q output that is available from outside. But for loading, you see there is no separate load control line, rather there are two control signals S1 and S0. Now, I can use, these are this S1 S0 combinations I am showing, this is S1 and S0. So, if they are 0 0, it means there is no change. 0 1 means right shift, 1 0 means left shift, 1 1 means parallel load. So, I can load it parallel, I can do a shift left, I can do a shift right, and the output is also available anyway. So, let us see how I can implement this. This can be designed in a similar way, in a way similar to a bidirectional shift register, but we need bigger multiplexers. There are 4 modes to be selected. So, I need to use a 4:1 multiplexer. So, you recall the multiplexer controls this S1 and S0, they were like this, 0 0 means no change. So, for the 0 input, the first one is the 0 input, this Q1 I am connecting here, Q2 I am connecting here, Q3 I am connecting here. So, the same value is getting stored, no change. 0 1 means shift right. So, for 0 1 this shift serial input right is being fed here, Q1 is fed here, Q2 is fed here. So, it is just like a serial shift right, and 1 0 means serial shift left. Here serial input left is fed here, Q3 is fed here, Q2 is fed here. This is shift left, and 1 1 is parallel load. You see D1 is fed here, D2 is fed here, D3 is fed. From outside data will get stored. Okay. So, this is how you can design a universal shift register. Well, an universal shift register is a circuit using which you can do all the kind of register operations, parallel load, serial input, serial output, everything. But in some specific application, you may be needing just a PIPO register or a simple shift register. So, you do not need all these multiplexers. So, if you really need, then you need to have this kind of a complex universal shift register, right. So, with this we come to the end of this lecture. So, in this lecture we talked about shift registers and the various different types of shift registers that are useful in some applications like ring counter, Johnson counter, then the bidirectional shift register and the universal shift register. So, we shall be continuing with our discussion in the next lecture, where we shall be talking about a fifth type of shift register called linear feedback shift register, and also we shall discuss some of the practical applications of these registers and shift registers. Thank you.